explain something that I just glossed over rather than breezing through this talk and having no one but me understand it, okay? This is the Monad Transformers talk. If that's not what you're here for, scramble. Okay, so let's get started. First off, there's a lot of code in this talk, and I'm not going to ask you to understand code on a slide or try to copy it from the slides that I've uploaded. So if you want to follow along or work on this at home, here's the repo. It's all there. This has slides in PDF, slides in PowerPoint, and the little tiny smallest stack project that has all of the code that we'll be working with today. So first thing you have to know is my friends have horrible senses of humor. When I told them I was doing a Monad Transformers talk, this is what they told me. What? Okay, there we go. Hi, Miriam. So another point that I want to make is if this doesn't give you the aha moment at the end of it, don't panic. Going over the definitions is nice. Having someone explain the definitions to you is wonderful. There is a component to learning this material that is just how much time have you spent thinking about it? How long has it been percolating in your head? So if this doesn't give you the aha moment, don't fret, don't despair, keep working at it. If there's one thing that LambdaConf in general can tell you, it is don't despair, keep working. This stuff is hard. This stuff takes years. That's fine. It's worth it. Okay. Yeah, like I said, it's like learning algebra or calculus for the first time. You're adding a new dimension to your understanding of the world. That takes time. All right. So the one-line summary of this is that monad transformers transform monads. That's it. You're done. Right? Go home, have pizza, talk to the other wonderful people at this conference. The tricky part is how. So I dance tango, and once you get past the, hello, this is your first day dancing tango, if you talk to anybody who has been doing this for a while, you say, great, I want to get better. Great, walk for an hour. Cover the fundamentals, cover the basics, then we'll get to the fancy stuff. So that's what we're doing here. Monoids, associative binary operations with an identity. Associative means that it doesn't matter if you have three terms that you want to combine. It doesn't matter in which order you do it. You're going to get the same answer either way. Binary operations are things that take two values. To contrast, something like exponentiation or absolute value take one. Addition, subtraction, list concatenation, a whole bunch of others take two. This is a requirement of this type class. The identity part means that there is some value for which, no matter which side of the operation is put on, you still get the other value. So some number plus 0 is still that number. Some number times 1 is still that number. Any list concatenated with an empty list on either side, you still get the same thing. Functors. Functors obey two laws. If you fmap ID into any structure, that's semantically equivalent to just running ID. You haven't changed anything because the only thing the functor should touch is the values in that structure, not the structure itself. So for example, if you have a functor instance that repeats a value in the list twice, that's a bad functor instance. Don't do that. The other one is if you fmap two functions into the same structure, you can just fmap once and compose those two functions. This is sort of getting into the same thing as fmap ID, where if your functor instance is doing something per application, instead of just taking the values and doing something with them, don't. Applicative. This one's fun. Oh my God! All right, that's a lot. I'll take it one at a time. So pure ID, splat v equals v. Much like the first functor law, this asserts that pure isn't doing anything sneaky on its own. The only thing that it's touching is its inputs. Or rather, the only thing that can touch it is the function that it's accepting, not pure itself. Same thing with fmap in our first law previously. Same here. If you have two pures and you're composing them together, you can just rewrite that as one pure with one function applied to the value. Does that make sense? Cool. And this is the same as the second functor law, because the full name for applicative is applicative functor, so it's going to borrow a lot from the previous one. Yes?
Can you go back a couple of slides?
Sure.
Right there, applicative side. But I don't really have to really
Okay, no, that's fine. So pure is it's a function that lifts a function into the context that applicative is working in. So if you're working on the applicative of lists, pure ID will give you a list with one value in it called ID. Yes? Okay, cool. The operator here, the splat operator, chevron star chevron, that's the applicative operation. That's the thing that applicative does. Okay? Okay. All right. We covered identity. We just got to homomorphism. I love that the font changes. I should fix that. Okay, interchange. So we have some value. We splat it with pure y. What if we swapped those two? Well, we have to do a little bit of syntax for the y. We have to add this $s, which I'll get to. But those two things should give you the same result, which is to say, evaluation order doesn't matter. You should just get the same result and not have to worry about accidental things like that. We're just reasoning through values, right? That was the whole point of Paul Snively's talk at the start of this whole thing. Let's have a concrete example to make things a little easier to understand. So we have pure of $5. I said I'd explain that a little further. Splatted with just plus 10, which is equivalent to it takes in a value and adds 10 to it and returns that value. So unsurprisingly, 5 plus 10 equals 15. And if we do it the other way around, 5 plus 10 still equals 15. And we can even assert, because Haskell is nice like that, that doing these two things is actually equal. There's no difference. I'm going to be having source links in this if you want to read further, because this is a lot to take in. Another way to interpret this is, like I said earlier, even if your functions have effects for doing side effecty things, order of evaluation shouldn't matter. And that's not trivial, right? Because if I say I have this function that prints a line to the log and then add 5 to a value, I want that, or if I've picked a particular order for that, I want that to stay put. So the fact that this is around is super, super helpful. Debugging Haskell code, if this wasn't the case, would be a nightmare. No one would write it. Well, maybe not no one, but. Okay, so what's with that dollar thing? Well, same as with the paren plus 5 being equivalent to I take in a value and add 5 to it, or rather plus 10. I take in a value and add 10 to it. This does something morally equivalent. If we look at the type of that, it says, well, I'm operating on a number initially. I have this function that goes from A to B, and then from that I give you a B. We can rewrite that, and GHC will agree, at least on the type level. The type names are different, but that's arbitrary. Who cares? They're the same thing. We can see that it lines up. Cool. Now, when I saw this the first time, when I was putting together this talk, I was completely lost. So if I saw this in Haskell code, I would want to comment for it. But here we are. All right, composition. So if we lift the compose operator, which here in Haskell is dot, right, f dot g, into this set of splat operations, that should be equivalent to this one here, where we've already evaluated this and we're just splatting this on top of it. Concrete examples will make this clearer. So if we evaluate this whole string, we get just 60. 30 plus 20 plus 10, right? If we do it the other way around, right? We did this way first, now we're doing it this way. We still get just 60. And we can even do the same trick before, where we evaluate both and then assert that they're equal. Okay, great, the law works, but how? Let's walk through that again. All right, so we have pure function composition splatted with just 10, splatted with just 20. Let's evaluate the first one first, just to simplify it down. So these two, this whole thing becomes just plus 20 plus 10. Right? This is inside the maybe. We have two functions, partially applied addition in both, being composed with each other. Okay, so that was part of the expression. Let's continue on down. Okay, 30 splatted with this whole expression. Well, that's going to give us 60. Math. Okay. Monads! Okay, so they must be burritos, they must be delicious, then we can swap out the burrito type with monadic burrito actions. Yeah, okay. I'm a clown. I'll admit it. So here are the three monad laws. We can return some value into a monadic context and bind that with a function and have that just be equivalent to applying that value to the function directly. That's left identity. We can have a monad and bind it to an empty return and not touch that monad. That's right identity. And associativity. So monad type signatures is I take some MA and I take a function that goes from A to MB and then I return that last MB. So here we have to do a little bit of manipulation to say, well, I have these two monads. I need to create an anonymous function around it that says I take in a value, apply that to one monad, and then bind it to the next. Or I can just write it how people normally write it. And these two there should be no difference between them. You should not be able to tell. Let's go through examples. Okay, so return A bound with K. So we have returning 5. So we're lifting 5 into whatever context we happen to be working with. And we have a function that takes in a value and then returns just that value plus 5. Well, we let that fall through and we get just 10. Right? Okay. Let's go the other way around. We have something that's already a monad, or I should say we have a value that's already in a monadic context. We bind it with an empty function, which is essential identity here, and nothing changes. Cool. Associativity is going to take a little bit more footwork. Let's define some functions in our imaginary REPL. So let's define f as something that takes a value and returns 5 minus x. I'm using subtraction here because that is not associative. So I want you to be persuaded that even though we're dealing with an operation here that is not associative, monads still preserve order of operations. And we can see that if we bind 5 to this function, we get 0. If we bind negative 5, 5 minus negative 5 is 10. Cool. Let's define another function in our imaginary REPL, saying g, lambda x is just 10 minus x. Now this is the function that we're ultimately going to be working with, which is return 5, fed through f, then g. And that's just 10. In this second one, I'm demonstrating to you that if order of operations is not preserved, we get a different answer. right? So this is a falsifiable test. This isn't just going to work accidentally because we happen to pick the right values. If Haskell gets this wrong, we will be able to see. Okay, so this is the first form, and this is the second. And they both give us just 10. Let's flip back to the, yeah. First form, second. And they both give us just 10. Cool, so that works. Another way to say this is using an operator that I've heard referred to twice, either as Quasi arrows or fish. I prefer fish. But this makes everything about these laws a little bit more obvious and transparent. You don't have to worry about, well, am I dealing with a function that takes in a value and then returns some other, whatever. Everything is level, right? But you don't see this too often. All right, let's take a look at bind. Now, category theory, I know, I'm scaring you just a little bit. But from category theory, we know we can define bind in terms of join and fmap. Fmap you've already seen. Join takes in a monad with 2 layers that match and peels one of those layers off. That's it. And we'll see what that's needed in a minute. So if we look at the type of bind, there's a, wow, I'm spacing, a constraint saying that M has to be a monad. We take in a monad. Our first argument is a monad of type A. We have a function that takes in that same A, returns a monad of type B, whatever that B is, could match, could not, we don't care. And then the final result is MB. Again, concrete examples. Let's make this a little bit more obvious. Reformat that. Now let's look at fmap. So the constraint here is functor instead of monad. It takes a function from A to B and an f of A and gives you an f of B. Cool. So we have a list of integers. We map show onto it. We get a list of strings. Yes?
Maybe this is too basic.
Sure.
But I'm still trying to understand the difference between monad and mono. You know, monad is, it has an identity element and it has associated array.
Sure.
And in monad, you have an identity element that is both right and left associated, as I understand, and it has associated array. So then what's the difference?
I'm trying to figure out how to answer your question. So monoid, okay, here's one. Monoid is dealing with just values. So I can have string. And I can say I can concatenate the empty string to either side, and I still get the string. Monad is about structures. So it's properties of things like lists, or maybes, or IO monads, or what's another good one? Eithers, yes, excellent. It's saying I can operate on things inside these contexts and still abide by a list of properties. So one is about values, one is about structures. Does that make sense? Okay. Yes, yes, very important. That's kind of the entire point, in fact. Okay. Close, is that, you understand that? Okay, so closed means if I have something, it means if I'm doing something with 2 domains, I can't escape it. Whatever I wind up with, I can still do this thing. So if you're dealing with functors are closed, for example. So if I have, I don't know why anyone would do this, but a list of maybes. I'm trying to create a functor instance. So I have a list of something. I want to fmap into that thing. I don't have to know that it's a maybe. I don't have to know that it's an either. I don't even have to know that it's another list. I just have to say, this thing has a functor instance. And then I can just reach into it. And oh, look, I've got a functor for this whole structure now. Because every element also has a functor instance. Closed. That's fine. That's why you're here. Okay. So these have something, like there's obviously some similarities here, but we're not done. So if this whole thing is join $fmap thing, let's look at what this does. Okay, so we have the same function that we were looking at before. It takes in an A, returns a just of that value plus 10. We fmap that into a maybe. Oh dear. This is not what we want. So fmap alone isn't enough. We knew that. This is why. But these are both maybes, just 20. We can call join on that and have there be no problem. And here, so flip. You have a function that goes from A to B to C. You want it to go from B to A to C. You want the order of the arguments to be reversed. Hello, welcome to flip. And in fact, we don't even really need to do this. There's another operator. So the previous one is arrow, arrow, equal. The other one is equal, arrow, arrow. This is just flipped bind. But we can see that we're using that category theory equivalence and getting the same values back, right? So it turns out category theory works. Surprise! Okay, so let's look at join. As I spoiled earlier, you have a monad, has to be the same monad, has to be nested twice, or peel off one layer. That's exactly what happened in this join $fmap call, right? Fmap returned join just 20. Calling join collapsed one of those contexts. And as one of the things I've been really hammering is that they have to match. So if I can call join on just 10, everything's fine. Just nothing, that's fine. Just nothing, it's fine. We're just peeling off one layer. We can even join lists. If we have a list of lists and call join on that, it just concatenates the values in the one layer deep, and we get the result. What if we try to call it on the list of maybes? Boom. It's very not happy with us. In fact, when I ran this error was repeated 3 times for each just. So GHCI was very not happy with me. So this won't work. We can't do this generally. All right. We know where the minds are. Let's try and make one for the simplest transformer out there, identity T. And let's try and make one step by step using that category theory equivalence. So let's start with fmap. We're going to define our arguments first. So we have a function that takes in an A and returns, as it should, an identity T of MA. I just picked maybe because it was easy. Nice and simple. We have a monad that we would like to mutate. So we do the naive, obvious thing and just say, oh, let's just do an fmap. And we get a horrifying, ugly, terrifying mess. We have identity T of identity T of just 20. None of the adjacent monads match. So we can't join anything here. This is a problem. We're screwed. We're only going to write Go for the rest of our lives. Ah! No, we're fine. It's probably not going to be the last time I throw shade at Go either. Anyway, we can make the situation a little bit more bearable, though. Monad transformers come with a function named run transformer name. In this case, it's going to be run identity T. And all that does is it takes in an identity T with some inner structure in it and returns the inner structure. It peels off the transformer layer. Now, one of the problems we had here was that this function, unhelpfully, was adding an identity T layer to our structure, which is what it should do. That's what the type signature of bind demands. but it's inconvenient for us. So we'd really rather it didn't. So first step is, okay, we have our fmap. And we have a function that we're calling. And we have the context we're lifting into. What if we said, run identity T, compose with whatever function we get? Well, okay, now we have an identity T of 20. It's not great, still not where we want to be, but we've made progress. Okay, well, what I really want to do is join these two justs together. But doing that around the identity T is kind of cumbersome. So since I'm building this up kind of like, you can tell I'm a system administrator at heart, I'm building this up like a command on the bash terminal. Let's run identity T on that result. So now we have something that is much simpler, and at the moment, not a monad transformer, which is just 20. Join will work on that. Okay, so now we have our MA. We're missing one thing for this to be like a law-abiding bind instance, which is we need to wrap identity T around the result. Now, please, love of God, don't write it like this. This is me deriving it while working with GHCI, saying, okay, this is what I have. What do I need to do to massage it into the shape that I want? Right? This is not what you ship. What you ship is something like this, where you just pattern match the values you want and squish them back together. Or, if you're really, really cool, you do this. Oh my God! Well, okay. This is out of the transformers library. So there's a lot of optimizations around it, which is kind of unfortunate, but that's the reality of production code. Let's look at the part that we care about. So return is lift whatever value we've gotten into the internal context and then wrap it in identity T. Makes sense. What we really care about is this bind instance, right? So let's just strip all that out and look at this. Let's look at each component and see what it tells us. So type signature of bind, this is kind of important. And we've seen equals arrow arrow before. That's flip of the normal bind that we work with. So type signature. So the K in this instance is the A to MB over here. And we saw when we were building up our fmap call, we need to pull the identity T out of the result that it gives us. That's exactly what this is doing. On the other side, oh, I didn't fix that. Oh well. So that's A to MB, which is what we want. We also have the monad that we got on the other side, but that's identity T MA, right? That M has two monad contexts bound up in it. So peel one off. And we can see that the function is A to MB. The run identity T M is just MA. Bind can handle that, but we're not done yet. We have to wrap that whole result in an identity T. Right? Cool, okay. All right, so that's a rough idea of how to write an instance for it, but how do we use it, right? We're not just writing instances, we're using it to do things. So identity isn't too useful. It just takes in what you gave it and gives it back to you. It doesn't have any effect, so it's not useful for a demonstration. Let's move to maybe. I have just a helper function that says print something and then read in what the user gives. I want you to note that this is a function from string to IO string. Keep that in the back of your mind. All right, so we have a function called getName, and it's of type maybe T IO string. It's a do expression with two expressions in it. It pulls input from my prompt with a name passed to it. And then it's an if statement saying that if you give me an empty string, something must have gone wrong, I'm bailing out. I'm returning a nothing. Or I'm going to build up the string inside this maybe context saying, well, you told me your name was this, in a new line. This doesn't compile. Let me give you a hint. Every expression in a do statement has to be the same type. This if returns a maybe t of IO string. This is IO string. Don't match. Bad. GHC is going to be angry with you. So let's do some type-driven development in Haskell. What we really want is a function that takes in an IO string and returns a maybe t IO string. Do I really care that it's a string? Well, not here. So we can just make that an A, because that doesn't really matter. That's an accidental circumstance of what I'm doing right now. The function that I want to magically appear doesn't need to care about that. Does it care about I/O? Probably not. We can just say that it's a monad and say that we're taking in this value that is a monad that has an A in it and add this other monad on top of it. And I happen to know, because I'm giving this talk, that there is a way to add a constraint to say that the other monad that we want to add is a transformer. And it's this very, very long, horrible mouthful. So we've asserted that M is a monad, that T is a monad transformer, and we're adding that T to the value we receive. That's called lift. This is the entire purpose of lift. So in order to make our previous function compile, we lift my prompt. So we have, transformed a monad from one monad type to another, right? It was IO something. Now it's maybe T IO something. Monads aren't interesting unless you have a bunch to work with. So let's make a few more. So we want get name, we want get number, and then get street name. You have to love my enterprise, data validation here. Okay. We can string them together like this. We can even do it with do notation, but it's actually noisier here. But how do you use it? This isn't an IO action. This is a maybe T IO action. We can't just say go do it. Well, there's a function for that. Run maybe T. All right. So this is our IO action. This could be our main, right? Main equals IO unit. We're doing it in a do block. We get the result of this by running run maybe T composition method. This thing here. Run maybe T on this whole thing. And then we say, okay, what result did we get? Did we get just? Okay, if so, print it to the terminal. If not, well, print error. Okay, live coding. This can't go wrong. Oh, yes, that would be a good idea, wouldn't it? That's not helpful. Can you read that? All the way in the back, yes? Okay, so the first one, I said, if it's an empty string, blow up. I was asking you for three things. As soon as one blew up, the other two stopped, returned a nothing to that function I called. It ran a case statement, said, oh, you got a nothing. I'm going to print you an error message. And I'm back at the terminal. what did I say? This was 7. And here's the successful case. So what effect did this have? This said, if any part of this process fails, just stop. Does that make sense? Happiness? Okay, well, that's all I've got. Questions? Really? None? Yes?
See how I can say this. Can you describe, like, maybe more abstractly?
More abstractly than Haskell? No, I'm kidding.
It's like, as a developer, I need to, like, eventually get everything out through I/O.
Mm-hmm.
Where my entry point is, and I'm dealing with all these, like, maybes and maybe, like, maybes within state monads, like crazy nesting of all these monads, and eventually you don't want to have to write a ton of code, pattern match on it, and then get your values up.
No, actually, the point of this is that, so the reason you use maybe T instead of just maybe is, let me look at the slides earlier. So, oh God, I'm not in.
Well, no, I understand that part. I was mostly, so you're lifting and you're running things. Like those are the two.
Right.
Transformer. Or is that actually in the monad transformer type class? Like lift and run.
So the thing that transformers do is, let's go. There's another example here. Let me see if I can find it. But you remember when we ran that first F map? No, this is it. Further. Here. So this happens generally. And if we, let's do the same thing that we did with lift, right? We're squinting out. The pattern here is that we have an F, a G, an F, and a G. The point of monad transformers is that by itself this can't work, right? We can't just keep binding, building up context, and then collapsing it down, because there's this thing in the way that's really, really obnoxious. So we can't solve it for FG generally, but we can do it if we make one of those things concrete. It says, I can't solve it for everything, but I can solve it right here, right now for identity T. And because I know this is identity T, I know how to pull one of those contexts out. And doing that anywhere in the structure would leave two of them adjacent that match. Well, except for the outer one, but that's not the one we're working with in the FMAP part. And at that point, we can just let bind do the rest of its thing. And so you can stack a whole bunch of them up. It's going to get cumbersome, probably. This is one of the reasons why people look down on monad transformers. And I haven't used this enough to have a concrete opinion on whether you should or shouldn't use it. I'm just saying this is how they work.
And here A is the number 10. How are you, like, identity T is a functor. I mean,
it's a monad, so it's a functor, yes. It has a functor instance.
It has a functor instance.
Mm-hmm.
How are you, like, double functoring?
Oh, I didn't cover that. So identity T has a functor instance where fmap is fmat.fmap. Surprise! Sorry, yes.
Okay, this slide is like...
Yeah, no, I knew I missed something. So
you know that within your monad transformer, whatever it's containing also has a functor instance. So when you do this, you know A is going to be...
Well, okay. You actually don't. So the way the functor instance for identity T and transformers in general say is, I have in front of me some identity T M, right? Because functor instance always leaves the last value unapplied. It's kind star to star. Because I have applied away this M, I'm going to insist that it has a functor instance on its own. So if I create like my own custom binary search tree, and I don't give it a functor instance, if I try to run fmap identity t my tree, Haskell is going to tell me, well, I tried to lift into this inner tree context that you just mentioned. There's no functor instance. I don't know how. And this is going back to the comment I had earlier with functors are closed. That doesn't mean you can just grab some other type and just make it be a functor. Well, I mean, you can if you derive it, but you have to derive it at least, or write it. Yes. Yes. So because you have two contexts, you're lifting, and then you're lifting into the inner one. Yes.
You mentioned monads and monoids and monad transformers, and you also mentioned paths and applicative notation rules for them.
Yes.
Can you elaborate more on applicatives?
Elaborate more on applicatives.
Give some examples, a little farther with that.
Not at the top of my head. I'm sorry. Brain check?
I can help you with that after it's done.
I love being around smart people. Yes.
So a question about when you use lift at the end rather than here. So when you went to the denotation and the first one was in
IO string.
IO,
It was result arrow.
ABC.
Right.
Yeah, can you just go back to this just a second? I think I missed something there. I'm sorry.
Yeah, no, absolutely. Yes, this is the broken one.
And you solved that by lifting my prompt.
Yes.
Is that correct?
So the result that compiles is lift $myprompt's name. I have the code here. You want me to try and build it with return? I'm kind of curious now. Okay, so does that work? Hey, it does. There you go.
Give me like a plain English intuition for when we lift, where we're saying that like we're lifting the whatever comes to the right of it up into like the category.
Category is a bunch of weird math stuff. I don't know that. So lift takes in a value of MA, right? It wraps that in some other monad. That happens to be, it wraps it in a structure that happens to be a monad that also happens to be a monad transformer. Yes, okay. Yes.
What do you do with three monads? So you had two monads, they don't compose, so you have a monad transformer that puts them the same type, and now you use both of them together, but what if you had a third or a fourth?
So what if I had like either T, maybe T, IO string?
Yeah, something like that.
Okay.
You just added one more. Like, does this, do monad transformers work for like n number of monads?
Yes, they do, and that's the point, actually. So the slide that I did not make that I should have is the zooming out a bit on the identity T just. What we really care about is the innermost two, right? Because in this context we have something that is in the way and then just with a just outside of it. So we need to get rid of that transformer, put these two adjacent, join one away, and then it's done. Whatever else is on top of the stack doesn't matter, right? At least in terms of bind. And because, two reasons. One, as we're working through, we're going to have that same FG problem again. And each transformer says, I know what I am and I know how to peel this piece off. So as we're walking through that very, very, very complicated transformer stack, each piece of it is going to have an instance that says, peel this off, put these two together, join one of them out, work into the next one. Peel the wrong one out, that created another structure for the inner one, put those two adjacent, join them together. Rinse, lather, repeat. Have I persuaded you?
To some extent. Like how would the code work? Like it would be, okay, so you have this monad transformer of two monads. Now you want to add a third in because now you have another operation that adds that type.
You want a reader T and a maybe. Right.
Yeah, so what's the next step? Like there's a new monad transformer that takes this monad transformer and this monad?
So what's going to happen, at least is what I expect, is so we have, let's put maybe on the outside because we want to be able to stop on a dime whenever something goes wrong. That contains a G. That G happens to be reader T IO string. That G is going to be repeated twice. And since we're operating at this particular part of the monad stack, we can say, okay, let's pull this maybe out so that we have, what is it? Reader T, IO, whatever, reader T, IO, whatever. And then each one of those is going to say, okay, well, I have the same problem. Let's pull off this either T. Let's pull off this reader T. Let's pull off this reader T. Collapse, collapse, collapse. Right? Until we're left with what we started with. Yes?
In your usage with monad transformers, are you dealing mainly with either T, IO, some custom error, and then whatever type you're dealing with? Is there a typical signature you use?
No, not really. It really depends on what you're working with. So the other thing is that order matters, right? So if I have, going back to your example, maybe T, reader T, something. That is a different effect than reader T, maybe T, something. Because when the maybe T says, oh, I'm sorry, something went wrong, won't it blow up? The reader T is going to still keep going. Whereas if those positions are reversed, the entire thing collapses. But what you're going to wind up seeing in production code is the function will say, I have this type signature of either a bunch of monads squished together or like a type alias for a bunch of monads squished together, depending on what that function needs to do. So the identity function, the identity T transformer, is an illustrative example, right? It just says, I take something and I give it back to you. Maybe says, I run this action, and if something goes wrong, I just stop. With either T, it says, I run this action. If something goes wrong, I stop and I tell you what happened. Reader T is I can let you read some data, but not modify it. StateT is you get the picture. Yes?
So you're saying that any team maybe has any team maybe, and then one of those is the concrete type?
Yes.
Which one of those in that stack is the concrete?
So when we're dealing with the bind instance, the transformer is the concrete type. Because we don't have to write a new instance for transformer maybe, transformer either, transformer either, transformer IO. Right? We can just assume that this is a monad, so if I arrange it in the right way, I can just collapse it down.
Because we can just FMAP because we know that.
And because our constraint says whatever I'm dealing with on the inside has to be a monad, otherwise none of this works. Right? Okay. I think I'm pressed for time, so I have to book. Yes, one more.
Is lift defined to lift all the way to the top of the stack?
No, it's one. Yes. Yes, in fact, I've seen examples of like an entire screen full in the editor of lift. No, it's just one layer. So if you have a whole bunch, it's going to be a problem. All right, one more?
Yeah, one other question. One thing I struggle with sometimes is if you have, let's say, either T, IO, customer, or A, if seems as if there's two failure monads. You could fail in the I/O or you could fail in the either. Can you talk about that a little bit?
I don't have the time for that. I'll get you after. Alrighty, I have to book. Thank you.